In this video, we are going to look at linear equations. We'll solve a couple of simple ones, and then we'll look at some applied linear problems, and finally look at the concept of what a zero is. So to begin with, when you solve any equation, and here's just some examples of equations we'll solve in this course, anytime you're solving an equation, what you're looking for is to solve for x. So x is equal to something. So on any of these questions here, what we're looking for is x is equal to some kind of a number. In each one of the equations, you would have different rules that you would use to solve that. For example, this one you can use the addition subtraction principle, multiplication division principle. In this one here, you would probably factor, or there's other tools you could use. This one you could change form. This one you might use synthetic division. This one here you'd use the arc sign in order to solve that, or there's other ways to solve that as well. But each type of equation has its own rules to solve them. So for linear equations, we basically use two different principles. So the addition subtraction principle and the multiplication division principle. So for example, for this first one, what I'm wanting to do, and anytime you're solving, you want at the end to come up with x is equal to something, right? So basically you want, here's the equal sign, you want x to be the only thing on the left side of that equal sign. And so right now you got to get rid of this minus 5. So the rule you would use is the addition subtraction principle. So to get rid of a minus 5, you could add 5. And if you do that, those cancel out. And so all you're left with an x is what we want. But you can't just add 5 to one side, you also have to add 5 to the other side. So in this case here, 17 plus 5, 22 would be my answer for that one. So that's the addition subtraction principle. Multiplication division principle, same kind of thing. I want to solve for x, so right now I want to get rid of this 1/3. What you could do is you could divide both sides by 1/3, but it might be easier just to multiply both sides by 3. Because if I multiply both sides by 3, these 3's cancel, and I'd be left with 1x, or just plain x. But if you multiply the left side by 3, you have to multiply the right side also by 3. Okay, so those are two principles that we use with linear equations. Sometimes we get linear equations that might look a little bit more complicated, like this one, and we'll see some other ones later. In the textbook, they suggest, and this is a good idea, that these might be some steps that you would want to do in order to solve this equation. So remove any brackets you have, do some collecting like terms, use a multiplication or division principle, and check your answer at the end. So this one, I am going to use that remove brackets. So to do that, I'm going to use the distributive property. So I'll multiply that through. Same thing here, there's a negative out sign, so I'll use the distributive property and multiply that through. Okay, now I'll collect like terms. 2x minus 3x is a minus x, and 2 take away 1 is a positive 1, is equal to 7. Again, I'm wanting to get x by itself, so let's get rid of this plus 1 here. So I'll subtract 1 on this side and subtract 1 on that side. That'll leave me with a minus x is equal to 6, but I don't want a minus x, I just want a plain x. So to get rid of that minus, or you could call it a minus 1 out front, is I'll divide both sides by a minus 1. Minuses cancel, so 6 divided by negative 1 is a negative 6. So let's check our answer and just see if we're correct. So I'm going to put a negative 6 in everywhere I see an x. 3 times negative 6 plus 1, and I'm hoping that's equal to 7. So negative 6 plus 2 is a negative 4, minus 3 times minus 6 is minus 18. Minus 18 plus 1 is a minus 17, I think. Okay, 2 times negative 4 is negative 8. Minus a negative 17 would be plus 17. Is that right? Equals, does that equal 7? That doesn't equal 7. What did I do wrong? Oh, I see what I did wrong. Right at the start. Oh, dope. Right at the start, I said that 2 times x is 2x, and 2 times 2 is 4. So this should be a 4. Darn. So 4 take away 1, this would be a 3. So I'm going to subtract 3 from both sides. I'm just fixing my mistake here. So this would be a 4. And then 4 divided by -1 is a -4. So let's put a -4 there, a -4 there. So it's looking a little messy. -4 plus 2 is -2. 2 times -2 is -4. Okay, and then 3 times -4 is -12 plus 1, that'd be -11. So this would be plus 11. And -4 plus 11 does come out to be 7. Perfect. It's almost as if I planned to make that mistake just so you could see how checking your answer helps to see whether you've done something wrong or not. Okay, so that's solving linear equations. Now, there's lots of different examples of linear equations and applied problems that use linear equations. I'll do a few examples for you. First off, I guess when you're looking at any kind of word problem, it's nice to have a strategy to use to go after the question. And the textbook suggests a nice way, and most textbooks suggest a similar kind of thing, that you familiarize yourself with the question, draw pictures, that kind of stuff, throw things into variables. Sometimes you might have to use formulas like these ones here to help you out. And then do the math, check your answer to see if you're right, and in the end say the length of the football field is 2, or whatever the answer comes out to. I'll try and use these steps as we go through some of the questions here. So they say the length of the largest regular soccer field is 30 meters greater than the width, and the perimeter is 460 meters. Find the length and the width. Oh, okay. So they say the perimeter is 460. So if they say in the perimeter, I'm automatically thinking that I might have to be using this formula here. And they also say that the perimeter is 460, so I'm going to put a 460 in there right off the bat. Then they say the length, so the length is 30 meters greater, 30 plus the width. So there's a relationship between length and the width, that the length is 30 more than the width. So what I could do is I could say, well, this is the width, and then this side over here is the length, but really, instead of calling it the length, I'm going to say it's 30 more than the width over there. And then I can use these two variables, or those distances, in my formula. So anywhere I see an L, I'm going to replace it with 30 plus W. 30 plus W plus 2 widths. And now I've got an equation with only one variable, and I should be able to solve for it. Distributed property, that'll be 60 plus 2W. Hopefully I didn't make a mistake on that one. So that would be 60 plus 4W is equal to 460. And then subtract 60 from both sides, so that would be 400 is equal to 4W. Oh, okay, now then we'll divide both sides by 4, and 100 divided by 4 is going to be 100. So it means the width is 100, and if the length is 30 more than that, let me just do that in a different color. So this is going to be 100, and the length is 30 more than that, so that's got to be 130. Let's do a quick check. So if the widths are both 100 and the length are both 130, that's a long football field. Anyway, 130 and 130 is 260 plus another 460 it comes out. So then at the end, it says find the length and the width. You could say the length is 130 and the width is 100. Okay, so there's an example. I'll do a couple more. So I've got some money to invest, and I invested at 5% interest. At the end of the year, I've got 2,400 bucks. So how much did I invest? Okay, well, I might have to use a formula like this, equals PI interest equals PRT. Might have to use something like this, that the amount that I have at the end is equal to a principal plus however much money I make with interest. Might have to use something like that. Might have to use a combination of those, because this is interest and interest is here, so maybe I could take that and plug that right in there. Yeah, that might work. So the amount I have at the end of the year is equal to the principal, the amount of money I put in, plus the interest that I made on that principal. And to figure out that interest that I made, I can use that formula. So it's the principal again, times whatever the interest rate is, times how long you had that money in for. And they say it's just 1 year. Now let's plug some stuff in that we know. So $2,400 is how much money I made at the end. Principal, yeah, I don't know what that is. Plus, I don't know that either. But the interest rate I know is 5%, and the time is just 1 year. So in rewriting the formula or the equation, this one here I could write as just 0.05 times p if I put variables at the end. Now these two are like terms. So it's 1p plus 0.05p will be 1.05p is equal to 2,400. And then I'll divide both sides by 1.05. So calculator, 2,400 divided by 1.05 equals, oh, did I do that right? No, that looks funny. I got 2285. I might be right. Let's try it. 2,400 divided 1.05 equals, yeah, I'm right, 2285.71. 22, that's a funny amount to have thrown in. 2285.71. So that would be the principal, that would be the amount that I invested. If I wanted to have a follow-up question would be how much interest did I make? And so you would just take the 2,400 and subtract the 2285.71, and that'll tell you how much interest you made. Okay, so that's another example in your equation. Here's another one. Cyclist leaves Lethbridge traveling east at 40 kilometers an hour, pretty quick. A car leaves an hour later traveling at 100. And the question is, when will the car catch up to the cyclist? And how far will the cyclist have gone? Okay, so it looks like I've got a rate. There might be a distance and a time. So this would be the time kind of thing. How far will the cyclist go? So typically in these ones, I like to use a table that helps me out. And the table will have the distance, a rate, and a time in it. And it'll have it for the cyclist, and it'll have it also for the car. So if they say, when will the car catch up to the cyclist, that would be the time when the distance is the same. So I don't know what that distance is, but I know that it's going to be the same for both of them. So I'll just call it D for both of them. Okay, the rate, the cyclist is going at 40 kilometers an hour, and the car is going at 100 kilometers an hour. Okay, for time, I guess I don't know. I'm looking to see when the car is going to catch up to it. So don't really know the time, but I do know the time would be an hour different, right? So a car leaves 1 hour later. So say the cyclist's time is t. That means the car's time will be whatever that t is minus 1 because it leaves an hour later. Okay, so there I've got two relationships. In this first one, and that's one of our formulas from the other page, there's a formula, distance equals rate times time. So for the cyclist, the equation I would get would be d is equal to 40 times t. And for the car, it would be d is equal to 100 times t minus 1. But the distances for both of those are the same. So if the distance for the cyclist is the same as the distance for the car, then this must be equal to that. So I can write that as a linear equation, 100 times t minus 1, and solve for the time. I'll do that distributive property again. So 100t minus 100 is equal to 40t. And I want to collect like terms, so why don't we subtract 40t on both sides? So I'll get 60t minus 100 is equal to, oh, there's nothing there, 0. Let's add 100 to both sides. And then let's divide both sides by 60. So it'll be 100 divided by 60, which would be 10 over 6, which would be 5 over 3, which is 1 2/3, or 1.67 hours. Okay, so the car would catch up to the cyclist after 1.67 hours. But then the question also says, how far will they both have gone? Well, I could take this number and plug it in everywhere I see a T there. So the distance that the cyclist went will be 40 times 1.67. And the distance that the car went will be 100 times 1.67 minus 1. So this would be 0.67, so 100 times 0.67. I think that works out to be 67. And then multiply this to these ones here, and that'll hopefully come out to the same distance. Okay, so there's a distance equals rate time question. Okay, last sort of worded problem is the triangle one. They say the perimeter of a triangle is 59. So the perimeter of any triangle is you would just add up the three sides. So side 1 plus side 2 plus side 3. And they say the perimeter is 59. Okay. Then they say the first side, let's call this our first side, is 7 centimeters shorter than the second side. Oh, well, I guess we could call this second side x. If that was x, then the first side is 7 shorter than that, so we would say x minus 7. Notice we wouldn't say 7 minus x. Whenever it says shorter, you typically would put the minus 7 last. And then the third side down here is 4 centimeters shorter, so it'll be a minus 4. Then double the first side. Well, here's my first side, so I have to double that first side and subtract 4. That'll get me my third side. Okay, so now I can plug all this stuff in. Here's my first side. So side 1 will be x minus 7, plus side 2 is just an x, plus side 3 is 2 times x minus 7 minus 4. And then suddenly I've got a linear equation just like we've seen before. Okay, the first one doesn't have a number in front of the bracket, so I can just drop it. Same thing with the second one. Here I'll have to use the distributive property. So plus 2x minus 14 minus 4. Now let's collect all the x's. So x plus x is 2x, plus another 2x would be 4x. Minus 7 minus 14 would be minus 21. Minus 4 is minus 25, I think. Is that right? Yeah. Equals 59. I'll add 25 to both sides. So this would be 84 is equal to 4x. And then I'll divide both sides by 4. So I think that comes out to 21. The question at the end here should have said, find all sides. So now I know x is 21. So this side is 21. Then this one will be 21 minus 7, or 14. And then this one, if this is 21 here, 21 minus 7 is 14. 14 times 2 is 28. And 28 minus 4 would be 24. And then hopefully if you add those three sides up, you come up to 59. And I think that you do. Is that right? 2, 4, yeah, comes out to 59. So those are some linear equation examples. The last section I wanted to show in this video has to do with zeros of functions. And zeros of functions are the x value when y is equal to 0. Graphically speaking, you could say that a 0 and an x-intercept are the same thing. Like if I have a linear function like this, that point right there would be an x-intercept, and you could also say it's a 0 because that's the point where y is equal to 0. So if you're ever trying to solve for a 0, basically what you do is you substitute a 0 in for wherever you see a y or wherever you see an f of x. So for this first equation or relationship, I'm going to put a 0 in right there for the y. And then I'll solve for x. So I'll add 5 to both sides and then divide both sides by 2. So 5 halves would be the x-intercept, or you could say it's the 0. If you have an equation or relationship written in functional notation, then I'm going to replace this whole thing with a 0. I'm not going to write f of 0. That's a different thing. That's looking for the y-intercept. But if they want to know what the 0 is, I replace that whole f of x with 0. Oops, that's a minus 3x minus 7. And then I'll add 7 to both sides, and then divide both sides by a negative 3. So the 0 for that function would be 7 over negative 3. Or you could call it negative 7/3. All right, hopefully that helps you with those linear equation questions, and also this application of that, solving for the zeros of the function.